Okay, welcome to section 3, which is now looking at probability trees. So question 15, sorry, the formatting here is a bit strange because it kind of goes on to the next page, but I'm sure we'll cope. Okay, so question 15 says this. Cards are either gold or not gold. The probability of getting gold is 0.05, which means the probability of not getting gold must be 0.95 because they must add up to 1. Hiram chooses a card at random and then he replaces it. So this is called unconditional probability because the probabilities, they won't change, because if you replace it, it goes back to normal again. He then chooses a second card, complete the tree diagram. So the question said, right, that the probability of choosing gold was equal to 0.05, which means the probability of not being gold, okay, must be 0.95 because probabilities, they must always sum to give you 1. So in each branch of a tree diagram, the probabilities must add up to give you 1. That just has to be the case. Now, because it said in the question that the card is replaced, that means on the second pick, the probabilities are going to be the same. So getting gold again is 0.05 and not gold must be 0.95. Again, if you choose not gold, and then on the second pick you go for gold, well, the probability is remaining unchanged, so it's going to be 0.05 again. So we've got 0.05, and the not gold, 0.95. Now notice a few things here, just to talk through on the first one. With tree diagrams, you've always got the same sort of layout. So we've got gold, and then not gold. We've then got gold, and not gold, gold and not gold. It's in the same order. You never switch the branches around. If you begin by going gold up here, you must go gold up here again. You can't then go and put not gold up here. It has to be in the same kind of order. And on each branch of the tree, so each like individual part, the probabilities add up to 1. Okay? So that's it on the first part. Part B then says, what is the probability that at least one of Hiram's cards is gold? Well, if at least one is gold, you've got a few options here. You might get gold and then gold. Okay, so you might get GG. Well, that's at least one gold. That's 2 golds. You might get gold and then not gold. Okay, so gold and then not gold. Well, that's still at least 1. Okay, what gold wants is at least 1. Or you might get not gold and then gold. Okay, so you might get not gold and then gold. That's still at least 1 gold. If you go no gold, then no gold, that's not at least 1. Now you've got to work out each of these probabilities, so that's going to do that. So the first one, to work out the probability of getting gold and then gold again, okay, well that's going to be, you just multiply them together, so it's going to be 0.05 multiplied by 0.05, which is 500 times by 500, which is 0. Let's put this into the calculator just to be safer. This is a bit awkward, isn't it? So if we times those together, just to be safer, let's get it onto the calculator. Okay, so 0.05 times 0.05 gives us this. Okay, 0.0025 is what that means. So we've got there we've got 0.0 0.025 on the first one. We've then got gold and then not gold, so that's going to be doing 0.05 times 0.95. So 0.05 multiplied by 0.95. Okay, and that gives us 0.05 multiplied by 0.95, which gives us 0.047 and then 5. Last but not least, we've got to multiply not gold 0.95 with 0.05, which is the same thing as the thing up here, but just in the reverse order. So it's going to be 0.95 multiplied by 0.05, which will again give you 0.0475. Now, to work out the total probability here of getting at least one of these being gold, you've just got to go and add these probabilities together. Okay, so we go and add gold, 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 not gold, not gold, and gold together. And if we add those together on the calculator, what do we get? Let's have a look. So 0.0025, add 2 lots of 0.0475, gives us 39/400ths, which is the same thing as 0.0975. So that should be the answer. Okay, 9. Oh, let's make it a little bit neater. Sorry, 0.0975. Okay, there we go. So clear at the end with the 5. And we can check the mark scheme. So this is question number 15B. So 0.0975 is correct. Okay, perfect. Good. We can move on. Question number 16, let's have a look, is this. And again, formatting is a bit strange here, apologies for that, but it says, question 16, a test can consist of 2 sections, A and B. 85% of people pass section A, so let's go on to the next diagram. Okay, so section A is up here, and 85% of those people pass section A. Now I'm going to write it as a fraction here. Okay, so section A that pass is 85% is per 100. I'm writing as a fraction because I know with tree diagrams, we always multiply the branches together, and multiplying fractions is much easier than multiplying percentages. It's going to get really confusing. Okay. Now, if 85% of people pass section A, that must mean that 15 people fail section A, because these, again, in each part of the tree diagram, these probabilities must add up to 1, and these do add up to 1. Okay, they add up to 100 hundredths, which is 1. So the first line, I've done that one. It then says 78% of people who pass section A also pass section B. So if they pass section A, which is this one up here, 78% of people, which they've written up here as 0.78, pass section B, which means the people that fail it, well, this part and this part must add up to 1. Now that's given to you as a decimal, so that's fine. Well, this must be equal to 0.22, because 0.78 and 0.22 gives you 1. Actually, because they've written these as decimals, I'm going to then change these into decimals. Okay, and 85 hundredths is the same thing as 0.85. So I'm going to change that to 0.85 and change this one to 0.15. Okay. It then says 36% of people who fail section A also fail B. Okay, so if they fail section A, 36% of people, okay, also fail section B. So if they fail section A, they fail section B, 36% is 0.36. And again, this branch here, this branch must add to give you 1. Well, this must be equal to 0.64 up here, because 0.64 at 0.36 gives you 1. There we go. So that's part A done. Okay. It then says 40% of people, let's zoom in a bit here. Okay, and get the tree diagram in the picture as well. There we go. It then says 40% of people who fail at least one section take the test again. Okay, so if 40% of people fail at least one section, well, that could either mean that they pass and then they fail. That's failing at least one, pass and then fail. Or you might go and fail section A and pass section B. Okay, if you fail section A where you failed at least one, or you might go and fail section A and also fail section B, double F. Okay, well that's failing at least one, because failing twice is failing at least once. So any of these people here take the test again. Now 5,000 people take the test, so how many of these people are expected to retake the test? So what you want to go and do is get the probabilities of each of these here, okay, and whatever that is equal to, find out what fraction it is of the amount of 5,000 people. So that's going to do this. Now you can actually do this in a much quicker way, right? To get the total of each of these individual probabilities, you could just do 1, take away the probability of passing and then passing again, because each of these probabilities pass, add pass, fail, add fail, pass, add fail, fail, must add up to give you 1 in total. But I'm not going to go and do that this time, just because I want to work through the method. So if we look at, so I'm going to get some more room on the screen here. If we look at the first one here, which is pass and then fail, that's going to be 0.85 times 0.22. So it's going to be 0.85 multiplied by 0.22, okay, which equals whatever it equals to. The next one is going to be equal to fast fail, 0.15 times by 0.64. So 0.15 multiplied by 0.64. And then last but not least, we've got 0.15 times by 0.36. So we've got 0.15 times 0.36. We're going to get each of these individual probabilities, we're going to add them together. Okay, so let's go and work through this now. So let's refresh this, and let's go and do the first one, 0.85 multiplied by 0.22. Okay, which gives us this, 0.817. Sorry, 0.187. We've then got on a second one, 0.15 multiplied by 0.64, which is 0.096. On the last one, we've got 0.15 multiplied by 0.36, which gives us 0.054. 0.054. Okay, now let's go and get rid of this actually, so it's a bit messy. Now, if we go and add these together, okay, well, this will give us the total probability of at least one person failing. So let's go and add those together now, okay, into our calculator. So refresh this and let's go and type in 0.187, add 0.096, add 0.054, and that gives us this, so 0.337. Okay, 0.337. So this here is the fraction of the amount of people who fail at least one test. Now to find this, because this is the same thing, isn't it? It's 337 over 1,000. Okay, so this is the same thing as 337 over 1,000. So you want to find this fraction of this amount, because 5,000 people take the test. If we multiply it by the fraction 337 over 1,000, that will tell you how many people fail the test. So times this number by 5,000 gives you 1685. Okay, and that should be the answer. So this is question 16, part B, which is, let's have a look at the mark scheme here. So the mark schemes are often a bit confusing. So okay, that is looking good. So yeah, it should be fine. Sorry, the mark scheme's not very clear here. Sorry, I can see the number 1685. I'm just double checking that is the final answer. 16B, method 1. Okay. God, it's really not very clear, the mark scheme. That's not very useful. Okay, perfect. That is correct. So we can move on. Okay, what's happened here with this one? Sorry guys, getting a little bit messy here. Okay, where's the question gone for this one? Heck, here we go. Right, question below, 17. Okay, question 17. You've got 2 bags contains only green discs and yellow discs. Bag A contains 1 green disc and 4 yellow discs, so that's going to be bag A, 1 green and 4 yellow discs. So bag A has got 1 green disc out of a total of 5 because 1 plus 4 gives you 5, and it makes sense because you've got 4 yellow discs out of a total of 5. That one's done. Bag B, you've got 3 green discs and 7 yellow, so you've got a total of 10, and 3 of them are a green out of 10, and 7 are yellow out of 10. And of course, bag B, the probabilities here, green and then yellow, they're going to be the same thing. So green again here is going to be 3/10, and yellow is going to be 7/10. Okay, so I think part A is just to work out. It then says, sorry, 1 disc is picked at random from each bag. Okay, so you pick something from bag A and from bag B. Part A is to complete the tree diagram with the probabilities, which I've done. Perfect. Work out the probability that both discs are green. This one's quite nice and straightforward. So just going to be getting green in bag A and then green again. We just simply multiply those probabilities together. So we go the probability of getting green and then green again is equal to 1/5 multiplied by 3/10. Okay, and 1 times 3 gives you 3. 5 times 10 gives you 50. So 3/50ths should be the answer. So 3/50ths, that's number 17, isn't it? So 16, 17, 15, 16. Okay, perfect, good. And that's it. Question 18 is this. A fair ordinary dice is rolled and a counter is taken at random from a bag. The tree diagram shows the probability, so that's on the next page, isn't it? So you've got a normal dice. Okay, even number is a half chance because, of course, on the dice you've got the numbers 1 to 6. And the even numbers are 2, 4, and 6, which is 3 outcomes out of 6, which is the same thing as a half, which is equal to 0.5, which is where this number comes from. And the same thing, similarly with odd numbers, it must be a half. And you've got the counters here being red, blue, or green. Okay, and then the same probabilities, red, blue, and green down here. How do the probabilities show that all of the counters in the bag, okay, so in the counters in the bag, are either red, blue, or green? Well, it's because the probabilities here, 0.1, add 0.3, and 0.6, they add up to 1. Yeah, so for this one, I'm actually going to go and type it up. It is because the probabilities add to 1. So 0.1, add 0.3, add 0.6 equals to 1. Okay, that is your answer. And I'm going to make it in red. So check it out. There we go. Color and then red. Okay, there we go. Oh, I think I read. Perfect. Good. Part B then says circle the probability that the counter is red or blue. Circle the probability that the counter is red or blue. Okay. Well, it's not saying whether you get an even number or an odd number. It just means that it's either going to be red or blue. Okay, which is 0.1 add 0.3. So it's a bit of a, what question are we on here? This is question number 18. It's not a trick at all, but so I'm just checking the maximum that is 0.4. Yeah, it doesn't want you to go and times anything here. It's not saying that you get an even number than like a red or a blue. It just is literally saying the probability that it's red or blue. Well, that's 0.1 add 0.3, which is 0.4. Okay, which is why it's this one down here. Part C, circle the probability that the dice lands on an even number. So the dice goes even, and then the counter is blue. So then blue over here. So even and then blue. Okay, so that outcome of getting even and then blue it's going to be 0.5 multiplied by 0.3, which is 1/2 times 3/10, which I'm just going to put it to calculator just to make it safe here. So that's going to go to, refresh that, 0.5 multiplied by 0.3, and that gives us 0.15. So hopefully that's one of the options, equals to 0.15, which we can see is down here. Perfect. Good. Question 19 is below. Question 19, Anna plays a game with an ordinary fair dice. If she rolls 1, she wins. Okay, so if she gets a 1, she wins. If she rolls a 2 or a 3, she loses. So let's make a note of this. That's going to be wins, loses. If she rolls a 4, 5, or 6, she rolls again. So it's going to be a re-roll. When she has to roll again, if she rolls an odd number, she wins. So if it goes odd, she wins. If she rolls even, she loses. Okay, complete the tree diagram with the 4 missing possibilities. So if you've got an ordinary dice, okay, again, the outcomes are going to be 1 through to 6. Now, of course, the probability of getting just the number 1, getting a 1, well, there's only one outcome here, so it's going to be 1 out of a total of 6. You've got 6 options here. A 2 or a 3, well, that's 2 options, 1, 2. So that's going to be 2 out of a total of 6 again. Okay, now this time, it's not as clear because the fractions have different denominators, but a half is, of course, the same thing as 3/6. And it does make sense because a 1/6 add 2/6 add 3/6 gives you 1. So the first roll, the probabilities add to give you 1, which is good. Now, if she rolls a 1, she wins, okay. When she has to roll again, if she rolls an odd number, which is either going to be a 1, a 3, or a 5, which is 3 outcomes out of 6, so even must be 3 out of 6, she rolls again. Anyway, part A is just to complete the tree diagram with the 4 missing probabilities, okay, which I've done. So this part is finished. Part B then says, is Anna more likely to win or to lose? Okay, well, let's find the probability. Let's find the probability that Anna wins. Now, to win, if she rolls a 1 straight away, so a 1, okay, she wins. So that is just one option, okay, and that probability is a 1/6. But we're going to have to add on something else to this, because if she also gets an odd number, if she gets a 4, 5, or a 6, she re-rolls, and if she then gets an odd number, she wins. Okay, so we either want this first option, which we've just done over here, which is a 6th, or if she gets a 4, 5, or a 6, she re-rolls, and if it goes odd, she wins. Okay, so then to get this probability of re-rolling and then getting odd, well, that's going to be this probability, which is a 1/2, times by this probability, which is a 1/2 again, because 3/6 again is equal to 1/2. So this kind of part of the tree diagram, this section, re-rolling and then odd, is a 1/2 multiplied by a 1/2. Okay, so it's going to be a 1/2 times a 1/2, which gives you a 1/4. Okay, so it's going to be a 1/6 at a 1/4, because you've got 2 options of winning here, 2 ways of winning. Now, 1/6 at a 1/4, common denominators, is going to be the same thing by times the bottom one by 4 and 4, and times this one by 6 and 6. We're going to get to 4 24ths, add 6 24ths, which is equal to 10 over 24. So the question says, is she more likely to win or to lose? Now, because 10 24ths, okay, this here is less than half of the things. It's less than 12 24ths, because this is the same thing as a 1/2. Right, it's more likely that she's going to lose. Yeah, because that's the probability that she wins is less than, if you get half of it, which is 12 24ths, 10 of them is less. So it's more likely, because of this statement over here, it's more likely that she's going to lose. Okay? You could also then alternatively say that because if 10 24ths is the times that you're going to win, 14 24ths is going to be the time that you lose. So you might also go and say 14 24ths is bigger than 12 24ths, so hence why you're going to lose. Let's just double check that one. Question 19 is quite a good question. Yeah, there we go. That should be fine, shouldn't it? So, good. Perfect. I think that's it, isn't it? So is that it for... It also then says you must work out the probability that she wins, which is here, isn't it? So, okay, we've just I'm going to rewrite it again, actually. So we've just stated that the probability that she wins is equal to 10 over 24, which is less than half of the outcomes, okay? Therefore, that means more likely she's going to lose, okay? And you've got the probability shown here. You could simplify it, but you don't need to, okay? And you've got the statement saying it's more likely that she's going to lose. Excellent. Right, that is the section on probability trees. On the next video, we'll look at Pythagoras and trigonometry. Okay, so that's it. Perfect.